For this month's Anklin talk, it's a pleasure to introduce Matt Patterson. So Matt is a postdoctoral research assistant at the University of Oxford Department of Physics, and he works on climate dynamics and predictability. At the moment, he's actually working on a European project looking at the effects of anthropogenic forcing and global warming trends on the scale of in seasonal prediction models. But actually, I've got a strong link with Matt's work. So he completed his PhD on the dynamics of the South Pacific split jet stream in the atmosphere.
Wow.
And this was supervised by Tim Willings at the University of Oxford, jointly with myself at the British Antarctic Survey. So his research involved understanding the factors that shape the variability of the jets and how they might change under climate change. Anyway, that's enough of me. Matt, please start.
Great. Thanks, Tom, and thanks so much for having me. It's really wonderful to be here and to be talking about stuff from the Southern Hemisphere and from my PhD again. Do just stop me if anything is unclear as we go through, because I know we're coming from a few different backgrounds. But today I'm going to talk about Southern Hemisphere atmospheric circulation and how that potentially might change with climate change. And particularly, I'm going to focus on stationary waves. And I'm going to argue that the tropics and the subtropics are particularly important in shaping how the stationary wave responds at high latitudes. But first of all, I thought it would be helpful just to think about what exactly stationary waves are and why do they matter. So quite simply, a stationary wave is any sort of zonally asymmetric feature of the time mean flow. So they're generally quite large scale features, and they're caused by flow of the air over orography. So for instance, in the Northern Hemisphere, the Rocky Mountains generate stationary waves, which affect the North Atlantic jet stream. They can also be forced by any sort of zonally asymmetric heating that could be caused by land-sea contrast or through zonally asymmetric SSTs. So for instance, you've got the West Pacific warm pool, which provides something of a zonal asymmetry in the Pacific. And why do they matter? Well, they determine the locations of storm tracks, the strength of surface winds. So in the Southern Hemisphere, we might think about maybe the sea ice edge or the amount of Ekman upwelling could be affected by the circulation. And stationary waves can also transport heat and momentum, although that's more important in the Northern Hemisphere than in the Southern. But we often think about the Southern Hemisphere as being quite zonally symmetric because of the circumpolar nature of the Southern Ocean. That is, there's very little land or orography in the way to disrupt the atmospheric flow. But it turns out that in the winter season, we get quite significant zonal asymmetries developing. So if you look on the left, this is a plot showing the 300 millibar wind, so the upper tropospheric wind, in the winter season. So that's June, July, August. And you'll see there's quite a bit of structure to it. So there's a strong subtropical jet, which kind of spirals around Antarctica. And the jet of the Indian Ocean splits into this subtropical branch and a polar front branch, forming the split jet. If we're to look at that in terms of stationary waves, so this is the stream function, but with the zonal mean removed, again in the upper troposphere. And you'll see that around Antarctica, it's really dominated by a wave one, so one peak and one trough, with some other components as well, maybe a sort of wave three component as well. But there's clearly some asymmetries to the flow. And this shapes the storm tracks. So this is work from Hoskins and Hodges back in 2005. And they looked at creating storm track climatologies by tracking storms using a few different variables. And you get different answers to the storm track climatology question, depending on what variable you look at. But the point is that regardless of whether you're looking at lower level vorticity or upper level vorticity, there's quite a bit of structure to the storm track a lot of zonal asymmetry. And so that's really the imprint of these stationary waves. So what causes these stationary waves in the first place? So I did some idealized experiments with Tom and as part of my PhD. And the sort of thinking behind this was, if you want to understand a system, sometimes the best way to understand it is to try and see what you need to do in order to break it. So what we did was we took an idealized model which represented the stationary waves at high latitudes relatively well. You can see this kind of wave one-like pattern in the control. And then we removed various aspects of the model which might contribute to the asymmetry. So one of the first things we did was we were using prescribed SSTs in this model, and rather than using the control distribution, which looked like that, we took the zonal mean in the tropics. So we removed the West Pacific warm pool and made the SSTs look a bit like this. And that's completely changed the structure of the stationary wave pattern, weakened it considerably. So it seems that tropical SSTs are able to generate a wave at high southern latitudes. So it seems that tropical SSTs are super important, and that agrees with earlier work by Inatsu and Hoskins. Also worth noting, we flattened Antarctica, and it turns out if you remove the Antarctic plateau, the stationary wave pattern is modified somewhat. So the kind of centers of action shift westward in that scenario. But again, it's not, the Antarctic orography modifies the stationary waves, but it's not fundamental to generating them. So now we understand a little bit more about Southern Hemisphere stationary waves. How might they respond to climate change? So the way that we investigated this was by looking at 36 coupled CMIP5 models. We looked at a comparison between the historical period from 1979 to 2005, and compared that to end of 21st century runs using the RCP 8.5 scenario. And that was really just to kind of understand the mechanisms, not necessarily, we know that RCP 8.5 may not necessarily be realistic, but it's still helpful to understand what's going on in the models. We also used a set of AMIP runs, so with prescribed SSTs from 1978 to 2008, as well as the AMIP 4K runs. So they're identical to the AMIP runs, but they have the SSTs over that same period, but uniformly raised by 4 Kelvin. And finally, we also made use of era interim reanalysis, which we sort of took as our observations. So we go back to the stationary wave pattern. This time I've shown it on a rectangular plot. And again, you can see that kind of wave one pattern at high latitudes. So what does the multi-model mean change look like? Well, it looks something like this. It's not a clear strengthening or weakening of the original pattern. Instead, it seems to be maybe something of a phase shift, and particular sort of notable anomalies include this cyclonic. So it's clockwise in the Southern Hemisphere. So we've got this positive anomaly kind of west of the Ross Sea and south of Australia. There's an anticyclonic anomaly south of Australia and over New Zealand, and particularly deep cyclonic anomaly to the west of southern South America. But generally, the anomalies tend to be a little bit weaker around the Antarctic continent. We can also look at this in terms of zonal wind. And this is kind of just to emphasize the difference between summer and winter. So in summer DJF, there's a really zonally symmetric jet response. So it's a real strengthening of the jet and possibly a poleward shift. But if we look at winter, which is the season that we're focusing on today, you can see there's much more zonal structure to it. So there's a strengthening of the westerlies to the south of Australia, and yet at other longitudes, the response is much weaker. So this, looking at these stationary wave responses in the models, we might have a few questions. So one of those is, are these changes sensitive to the pattern of the SST change? So I've argued that tropical SSTs are important in generating the stationary wave pattern in the first place. So they may well be important in changes to the stationary waves, but that could pose a problem because tropical SSTs in models don't capture the trends of the last few decades particularly well. So we might have a little bit less confidence that the models will do something sensible looking into the future. So one thing we might want to know is the particular changes that we're seeing, are they sensitive to the particular pattern of SST change, or are there other things at play? Secondly, because we're Anticlim, we're interested in what's going on at high latitudes. And so one question we might ask is, how confident are the models in the changes at high latitudes? We saw there that actually some of the changes were quite weak at high latitudes. So is that a case of the models are all showing a weak change, or are the models just showing different changes and they're kind of cancelling out? And then finally, what are the real fundamental drivers of these stationary wave changes? Can we try and understand those a bit more? So I'm going to answer these first two questions first, and then we'll get to the last question after that. So how robust are the stationary wave changes with respect to the SST pattern? So this is the pattern of SST change in the end of 21st century runs, and you'll see that it's quite El Nino-like, so a particular warming over the central and eastern Pacific, with a relatively slower warming over the South Pacific. But again, we're not necessarily confident that that is exactly how the real world will behave. So one thing we can use to try and understand this a bit more is the AMIP 4K runs. So in these runs, the SSTs have just been uniformly raised by 4 Kelvin. And you'll see that there are some features of those models that are actually quite similar to the RCP 8.5 runs. So you still have that sort of land-sea contrast. So as the SSTs are warmed, the land warms up faster. There are also features like the tropical upper troposphere warms faster because of the coupling between the surface and the moistening of the atmosphere. So through the moist lapse rate, that warms the upper troposphere faster. And also there's a jet response in it as well. So there's a lot of similarities between these two runs. It's just that this one is a bit simpler. So are the stationary wave patterns similar between these two runs, or are they quite different? So I've shown at the top panel the figure that I've shown you already of the stationary wave change. And here I've actually included hatching to indicate model agreement. So any place that I've got hatching, at least 80% of models agree on the sign of the change. So you see that in a lot of these places, such as this region, this cyclonic anomaly to the south of Australia, there's really quite a lot of agreement between the different models on the change. And again, this region to the west of South America, but less so in this Southern Ocean region down here. If we now compare that to the AMIP 4K runs, there's actually a lot of similarity between the centers of action, and the overall pattern generally is very similar. So again, we've got that cyclonic anomaly to the south of Australia, we've got anticyclonic anomalies over Australia, there's a kind of dipole to the west of South America. So it seems that although that there are a few subtle differences, as we might expect, fundamentally the pattern is very similar. So it doesn't seem to be dependent on whether it's an El Nino or a La Nina-like warming. It just seems to be that warming the SSTs uniformly will give you quite a similar result. So that's really helpful to know. Now let's have a look at what's going on at high latitudes. So I've said I've got 6 models here, fairly randomly chosen, but they hopefully are representative of the 36 different models that I've looked at. And you'll see that there are some regions in which the models really agree quite strongly on the sign of the change, whereas there are some regions where that's not the case. If you look at the solid boxed regions, so this region to the south of Australia and this region to the west of southern South America, you can see that in each of these cases, there's mostly red, mostly sort of cyclonic anomalies in each of these boxes. So it seems to be that there's a fair, that it's fairly robust, the change across models generally. But if we then look down at the Amundsen-Bellingshausen Sea, just near the Antarctic Peninsula, there are very different responses across the different models. So say, for instance, the MPI model shows a very cyclonic response, so clockwise, whereas the IPSL model shows the exact opposite, but very strong response. So it seems that when we look at the multi-model mean, actually all of these responses are cancelling out. So can we understand this a little bit more? Well, it turns out that actually the historical bias in the stationary waves has a huge impact on the response in this region. So what I've done here is I've calculated a bias index by looking at the root mean square error from the from era interim observations between 50 and 70 south. So I've looked at the high latitude stationary waves basically, and created a composite of models which have a high bias. So that's these models, and a composite of I think it's the 7 models with the lowest bias. In the high bias models, the response is very wave 1-like. So there's again the same cyclonic anomaly to the south of Australia, but there's an anticyclonic anomaly here in the Amundsen Sea. But if we compare that to the low bias models, it's much more of a kind of wave 3-like response. And I think I haven't gone into more detail on this particularly. I need to maybe look at this again, but it seems that the high bias models particularly seem to have a very equator jet. So it may well be that the sort of path, the propagation of the waves is slightly different in those models. But it seems that the stationary wave could almost form like an emergent constraint on the response in the future. So that's potentially quite useful information, and it's maybe much more likely that the response in this region will be cyclonic rather than anticyclonic, based on the bias. So we've looked at those first 2 questions. Are these changes sensitive to the pattern of SSTs? Not fundamentally, even if the details may be. And in terms of how confident we are about what's going on at high latitudes, well, the stationary wave change is a bit sensitive to the historical bias in the stationary waves. So finally, let's have a look at what factors are actually driving the stationary wave changes in the first place and try and understand that. And to think about this a little bit more, if we think about stationary waves, they're basically Rossby waves in the atmosphere, and there are 2 ways in which they can change under climate change. One of those is changes to the source. So say they're forced by diabatic heating in the tropics and subtropics. If the strength or the kind of shape of that source is changed through climate change, then that could change the stationary wave pattern. Or secondly, changes to the background state. So the background state winds. If the winds change, the propagation of waves is determined by the background state. And so say the jet strengthens or moves polewards, that may, also affect the propagation of waves. Now, I'm going to argue that it's actually the first that is most important, and that's what I'm going to focus on for the rest of this talk. So changes to the source of the stationary waves. So one good diagnostic to look at the source of stationary waves is something called the Rossby wave source, and I've plotted that here for the historical climatology in this upper panel, and the change in the RCP 8.5 runs in the bottom panel. Now you'll notice that basically if you compare these two plots, the general pattern in the tropics and subtropics is a weakening of the Rossby wave source. So anywhere you see green here, you tend to see a brown color. Anywhere you see brown, you tend to see green, and so on. And again, I've shown hatching to show where models agree on the sign of the change. So it seems over this southeastern Pacific region, there's a particularly robust change across models, whereas other regions such as the Indian Ocean, which have a really strong Rossby wave source in the climatology, don't show that same sort of robust change. So this seems like it could well be an important region. And in fact, if we take those particular Rossby wave source changes from each of the models and correlate them with the stationary wave patterns, the stationary wave patterns of change across the models, these two boxes are associated with patterns that look like this. So like that. And they actually, when you compare panels E and F to the multimodal mean change, there's actually quite a considerable resemblance, particularly between this the Rossby wave source change at about 20 south and the stationary wave change that's associated with. So it seems just from a sort of simple correlation analysis, there seems to be some correspondence between the Rossby wave source change and the stationary wave change. But we can test this using a simple barotropic model, so a simple kind of one-layer model of the atmosphere. So we've got the barotropic vorticity equation. So zeta is the absolute vorticity. We've got linear damping and hyperdiffusion just to remove small-scale variability. And what we can do is force this model to have a background state which exactly matches the historical background state for a given CMIP5 model. So we force the model to have a background state that looks a little bit like this. Then what we can do on top of that is add the Rossby wave source change between the RCP 8.5 and historical runs for that given model, and that looks something like this. So again, if we just add the change over the South Pacific, and then we add this into our model and just let it evolve, and that should become stationary after some period of time. So if we do that, we can do that for all of the different models. I've just shown 4 here. On the left-hand side, we've got the RCP 8.5 minus historical, so the full model response. And then I've got the equivalent barotropic simulations on the right. So just by adding the source, the Rossby wave source change over the Southeast Pacific, we can actually reproduce many of the stationary wave changes across the different models. So for instance, the BCC model has quite a strong wave 1-like response at high latitudes. So this cyclonic anomaly here and anticyclonic anomaly here. And if you compare the two, that's pretty much what we see in the barotropic simulation. Now the centers of action are not quite in the right place, but apart from that, it gets it pretty well. Equally in the EC Earth model, which shows a slightly higher wave number response, there's also it's also pretty well captured by the barotropic simulations, even more so for the GFDL model and for HADGEM2. So it seems that not only can these barotropic simulations capture the overall response pretty well of the multimodal mean, it can also distinguish between those different simulations in terms of the strength and the structure of the Rossby wave source forcing. And I think it's instructive to kind of look at how that wave response actually develops in the barotropic simulations. So what I'll do in the next figure is I will take the HADGEM2 barotropic simulation and look at how that develops. So if we do that, so basically we've got our historical climatology, which we've imposed. We impose a source over the Southeast Pacific, and on day one, this is what it looks like. So we've got an anticyclonic anomaly here and a cyclonic anomaly here. And as we kind of step forward, we've got a wave which propagates southeastwards. And that continues to do so, but then at high latitudes, we also get a wave which begins propagating westwards. So very low frequency waves can propagate westwards. And as we continue to step through that, we see a kind of anomaly is broken off here, and that pattern just strengthens over the next few days and eventually becomes steady after around about 2 weeks. So just to sum up there, the Southern Hemisphere winter response to climate change has a significant wave one or stationary wave-like component to it. So while in summer it was very zonally symmetric, in winter it's much more zonally structured. And this pattern of stationary wave changes doesn't seem to be particularly sensitive to the structure of the SST pattern change. But the high latitude response does depend quite considerably on the historical bias in that particular model. And we've looked at what's driving these changes, and it seems to be that a change to the Rossby wave source, or the source of stationary waves, over the South Pacific, which sort of drives these changes. And we've shown that through sort of regression correlation analysis and barotropic model experiments. But there's still quite a few unanswered questions and lots of further work to do on this. So in terms of what are the mechanisms behind the changes to the Rossby wave source in the tropics, we don't really fully understand that yet, and why that's so consistent across models. And also, I've only looked at the end of the 21st century, what happens in the period between 2020 and 2070. What about CMIP6, other scenarios? Still lots of other interesting things to find out there. And if you're interested in finding out more about this, we've got a paper on this from 2021 in Journal of Climate. So thank you very much for listening, and I'm happy to take any questions if anyone has any. Thanks.